Yeah, okay, I think the recording's on and we can get started.
Okay, good afternoon, everyone. My name is Martin Min. I'm from Department of Machine Learning, NEC Laboratory of America. It's my honor here to give the guest lecture on deep learning. So there will be like 3 guest deep learning lectures. So this is the first one about introduction. So there are several different topics like a deep learning, representation learning, and machine learning, artificial intelligence. You can see that deep learning, it is a subfield of representation learning, and representation learning is kind of like a sub area of machine learning, and machine learning is an area in a broad topic of artificial intelligence. What is data science? You can see data science have great overlap with the deep learning, representation learning, machine learning, and artificial intelligence. That's why I think deep learning is a very important topic in data science, especially in biomedical data science. So let's see some kind of Google trends. You have already studied support vector machines. You can see the Google trends for the SVM. So in 2000, before 2010, SVM is very popular. But after 2010, you can see deep learning starts to take off, and it's even more popular than SVM. So we add another term, machine learning. You can see machine learning is become more and more popular since 2010. And data science, you see, machine learning is even more popular than data science. So this is the trend of AI, a buzzword AI. You can see that the AI is always popular from the early 2000 to now. And there is a big spike in about like 2012. So what happened in 2012? Actually, in 2012, there is a challenge called the ImageNet challenge in computer vision. In that ImageNet challenge, a deep learning method based on convolutional neural networks gets the best performance on this challenge. So you can see that before 2012, we have on this ImageNet challenge for recognizing classifying the images into 1,000 different categories. The most popular model are either based on sparse coding or based on some kind of handcrafted features. For example, the NEC Labs America model is the champion in 2010 and based on sparse coding. But in 2012, we almost halved this kind of error rate based on deep convolutional neural networks. That's why deep convolutional neural networks becomes the hot topic in 2012, and everyone excited about the deep learning and AI. So we can see the AI revolution is actually driven by the deep learning development. So the artificial intelligence based on the deep learning has also been used a lot of different areas. For example, the speech recognition. You probably have the Amazon Dot, Alexa Dot, or the Google Mini at home. You can talk to your Alexa, and then you can see that the speech recognition is so useful, and then it can almost understand my broken English, without any difficulty. But before 2012, before the deep learning takes off, and then the speech recognition performs very bad, even if for native speakers, and makes a lot of mistakes. And for machine translation, deep learning has also played a major role in the machine translation. For example, in Google Translate, and then you can nowadays you can easily translate the Japanese to English, English to French or whatever. If you don't know any a foreign language, there should be no problem anymore. And then you just take a picture and then you upload it to Google or even WeChat. They can translate it for you immediately. This technology is also based on deep learning. Actually, it's called the model we will talk about it. It's a sequence-to-sequence model. The deep learning, the AI-driven by deep learning also plays an important role in games. For example, in reinforcement learning, deep reinforcement learning, they use the deep learning to learn an important network called the policy network to play the Go game and video games. For example, in this, I will show you a video of this using the deep reinforcement learning for playing the breakout. So in this framework, actually, the network is trained by a deep neural network, the policy network, just like for, by watching this screen, the game screen, and then you need to decide what to do. And then that kind of like action given the screen is trained by deep neural network. You can see in the beginning, the network is not trained very well. So, the agent doesn't know how to do it well. But you see after 2 hours of training, it plays pretty much like an expert. So we should notice that, the agent, this deep neural network has no idea about this game. You just give me the screen as input and then give me assign the reward. They will learn this kind of policy network, giving the pairs of like the reward, and this kind of like the screen. Of course, in the reinforcement learning, the reward is not, you can see that it can eventually learn how to tunnel this game, and then so that's pretty amazing, very amazing, I would say. So the deep reinforcement.
To support local restaurants, we've been to every city, including Little Rock and even Worcester. And tonight,
This is I will show. So the deep reinforcement learning based on the policy networks learned by deep neural networks has also been used for the Go game. So in 2016, the AlphaGo with the policy network trained based on deep learning beats the Go grandmaster DC Dao, and then there's a Nature paper and then published in 2016. And after that, Google DeepMind improved their algorithm. So the policy network, for policy network deciding which stone to place based on the pixel input of the board, and then they do not need to train without the pre-training. It means that it doesn't need to pre-train this network using the expert moves, and then they just play the Go game by itself. And then so the deep reinforcement learning with the policy network can learn how to beat the original version of the AlphaGo that beats like DC DAO. So deep learning has also been used for molecular and drug synthesis. For example, there is a Nature paper published in 2018 about planning chemical synthesis with the deep neural network and symbolic AI. So the deep neural networks in all these kind of previous games, the deep neural networks has been trained to play the game with the complete information. It means that you need to know that you have the perfect information about your components. But in poker game, we know that some information is hidden, right? And then when we play the poker game, we do not know exactly what kind of like a poker cards my opponents have. But deep reinforcement learning can also be extended to play the poker game. And then there is a Nature news saying there is a Nature paper and then seen as the published the results by the CMU, and then they use a deep reinforcement learning to beat the poker expert. So there's Nature News about like how rival bots battle their way to poker supremacy. So, and this kind of deep reinforcement learning with the imperfect information game can also be extended to deal with multiple players. For example, there is a Nature News in 2019 said no limit. The AI poker bot is first to beat the professionals as multi-player game. So the deep reinforcement learning with the deep neural networks trained as the policy network means choosing an action based on the input, not only being used for playing these kind of board games, has also been used for playing the strategic games. So I will show you a video.
Artificial intelligence researchers at DeepMind have mastered Pong, chess, and Go. But some games are on another level.
The game of StarCraft 2, one of the most complicated video games ever created. It is a real-time strategy game, which means that you don't take turns, you play, and you have to play fast.
Oh God, pushing this back in. He's gonna kill off MVP here. Oh, he kills off the mothership core. He is everywhere.
It was clear that StarCraft would be a great grand challenge for us to tackle using an artificial intelligence, the techniques we love, namely neural networks, deep reinforcement learning, and so on and so forth. My name is Oriol Vinyals, and I'm the lead researcher of the AlphaStar project.
AlphaStar is an artificial intelligence system that plays the game StarCraft 2.
So the first element of StarCraft that's quite different is that you don't get to see what's happening on the other side of the board. That is what we call imperfect information, and is a key challenge that neither in chess or Go are present. Another key difference is that the pieces of chess, or what we call units in StarCraft, are created throughout the game, right? So you start with very, very few units, and what you're doing is deciding which pieces are you going to invest in creating next. And that's very important because at the same time, you must counter pieces or units that the other player is thinking about without having perfect information. The first step of AlphaStar is, can you predict where a human is going to click? What's the most likely move? So essentially, AlphaStar is gathering information from the game where all its units are. It's getting all this data into not a program, but rather a mathematical entity that is called neural network that is able to then process all this information. We never hard-coded what this processing means. This was fully learned from first imitation learning, trying to imitate human moves, and later on self-play through the AlphaStar League. And after this processing, many layers of computation of learned behavior at the top, there is essentially a single action that will be sent back to the game. And so this action could be create a new unit, create a worker, send this worker to scout, move the camera to this location. And that's essentially what AlphaStar is. Every basically 20 milliseconds in the game, and every action you see here is a result of computation using this neural network.
By January 2019, AlphaStar was able to beat 2 professional players under special test conditions. But people wanted to see if it could reach the Grandmaster level, beating the best players at the full game.
What's quite critical is that humans are very creative at playing this game. So once we went online with this agent, we faced all sorts of creative strategies that we could not possibly have ourselves designed. So the very first game that we entered, we were playing against obviously someone we don't know. So it really was like a lot of adrenaline and a great moment to let people essentially experience what it is to play against such a strong AI.
AlphaStar progressed by playing against itself, against a range of human players, and crucially, by playing against other AI agents.
We have this league of agents where all the agents are doing self-play in a manner that is perhaps a bit more advanced than what has been done before. And there we did perhaps the most research advances in the last few months, in which we discovered that it's not sufficient to have only one agent that its sole purpose is to beat itself and its past versions of itself. It's very important to add agents that find flaws in the main agents, right? So we call these agents exploiter agents. And if you will, it's kind of asking for a friend to beat your current strategy. And maybe this strategy that is going to beat you is not a great strategy in isolation, but it's certainly going to help you become a better player. And that core idea, plus then some extra developments in imitation learning and reinforcement learning that we had in the project, created an artificial intelligence agent that can play the game of StarCraft 2 at a grandmaster level. Actually, I used to play the game back in the 90s. I played quite seriously the first version of the game. One of the sad things that happened is that I kind of waited too long to play against AlphaStar.
Okay, so let's continue. So you can see that in the deep neural networks, as the policy network for the deep reinforcement learning can play the board game with the perfect information and the poker game with the imperfect information, or even the imperfect information game for like a StarCraft 2. And then because you don't know the information about your components of multiple players, and also the time range is much longer than that's the poker game, because it's a long it's much more difficult. So the deep learning has also been used for training for training the language models. For example, the powerful language model called the GPT-3 with a deep neural network with a attention mechanism called transformer. This kind of generative model can generate a novel. For example, you just like say the Legolas and Gimli advanced on the orcs, you starting from this sentence, and then this generative model of the natural language will complete everything. And then you can see that they can write a pretty good novel with some kind of like a semantic meaning and human intelligence in it. So it means that if we train our deep neural networks with enough model on the sentences and the Wikipedia corpus, and the natural language generative model can even mimic the human semantics intelligence. So the Science journal also reports algorithm called the create movies from just a few snippets of text. This project is actually my project, and then you just input a sentence saying like a human is walking on the sea, and then my algorithm will actually create a short 3 seconds movie about the human actually walking on the sea, and looks almost like a real. So this human face is not real. It means that it doesn't exist. So, but you can see that it's actually it's generated by a generative model of images. You can see this person looks pretty like a natural, right? And then they have the white hair and the wrinkles of the eyes, but it's just like it's actually a fiction person image. So it's just based on the deep neural network trained on large amounts of face data. So deep neural networks, although the deep neural networks have been so powerful for playing the board games and then for generating data, generating novels, generating faces, but it can be easily fooled. For example, all these kind of the images on the left columns are the actual real images. So this is a school bus, and this is a tower, and then this is a chicken, I'm not sure, and a bird. And then if you just add some kind of noise that is imperceivable by the human, and then all these kind of like images on the right column here will be classified as ostrich. But when you look at these images, clearly this is a dog, this is a building, tower, and this is a bird, and this is a school bus. But the deep neural networks will very confidently predicting these classes as ostrich with about like more than 95% of confidence. And also, this is clearly a stop sign. But if you just put a sticker on the stop sign, the deep neural network will predict it to be something else. It cannot recognize this stop sign anymore. So the Forbes report says that the AI is not similar to human intelligence. Thinking so could be dangerous because the deep neural networks are not robust, although they can they can achieve amazing results in many different applications. Stephen Hawking even says, AI could be the worst event in the history of our civilization. So I don't personally agree with it. So let's uncover behind the scene. What is the driving force of all these kind of amazing applications? It is deep learning. So the deep learning drives all these kind of technology advancements and is also the root cause of all these controversial debates and potential dangers. So what is deep learning? So deep learning is just a subfield of machine learning. So what is machine learning? The machine learning is about teaching computers to perform tasks by only showing them the data examples without explicitly programming, without any explicit programming instructions. So machine learning, data science, and computer science are more and more related to each other. Sometimes you cannot distinguish this topic is machine learning or data science. I would say they are almost the same, in many different scenarios. So machine learning, what is machine learning? So traditionally we program computers and then teach the computer. We just program the computers to perform a lot of tasks. For example, if we want the computer to identify a dog in an image, and then we need to explicitly write a program and then say what does the ear look like and what the eyes of the dog look like, and then we run that program, and then that kind of program can recognize that dog. But machine learning is different. Machine learning lets the computers learn to program by themselves, but we just need to show the computers some examples. So in machine learning, there are several important components: the feature representation, objective function, and optimization. So we define some good feature representations for some data points, and based on a collected large set of data points, and then we define a reasonable objective function, and then we optimize this objective function on this kind of large amount of data set, large amount of data points collected, and then we can hopefully we will have a algorithm model trained, and then we run this model on the test data. Hopefully it will have low generalization error. It will perform as well as on the training set we have. So there are three types of machine learning tasks: supervised learning, unsupervised learning, and reinforcement learning. So the supervised learning is that you give in the training examples of the input feature vectors and their corresponding target outputs. We want to predict the outputs given the inputs. For example, we have the classification, regression, or time series prediction. So in unsupervised learning, we only have the input feature vectors. We just have the data. We don't have any label. So we usually use the unsupervised learning to automatically discover the hidden representations or structures in the data. For example, we perform clustering. We find the clusters, we assign each data point in a different cluster, and we do the data compression. We want to compress the high dimensional data into low dimensional space, or compress the large, the redundant information, remove the redundant information in the in the data. So compress the high-dimensional data in a low-dimensional space such that we can also reconstruct the original high-dimensional data, or we can perform some kind of anomaly detection, outlier detection. So in reinforcement learning, it's different from the supervised learning and unsupervised learning. There is a unique characteristic of the environment. You put your program in an environment, and then your program interact with the environment, and then it gets the input from the environment, and then you take some action based on your observation of the environment, and the environment will give you some reward. What your program do is that you want to learn a network, an interaction network, by observing the interaction network, just predict what kind of action you want to perform given your current observation of the environment, and then such that you will get your reward maximized. So it means that you want to maximize your expected sum of future reward, and then to by learning a function that predicts actions given the current observation in the environment. So this is in the unsupervised learning and the supervised learning. There's no interaction. When you give the data, the static data, the data is already given. But in the reinforcement learning, because your program can interact with the environment, you can get as much data as possible. But you don't have the direct supervision, because when you interact with the environment, sometimes you do get the reward, but sometimes you don't. So it means that your supervision is actually sparse. So this is the difference between the reinforcement learning and supervised learning and the unsupervised learning. So for supervised learning models, for example, we have the linear regression, logistic regression, naive Bayes, linear, LDA, k-nearest neighbor, SVM, decision tree, random forest, multi-layer perceptron, neural network, deep learning, conditional random field. For unsupervised learning, we have, for example, the k-means clustering, the Gaussian mixture model, hierarchical clustering, PCA, ICA, or vector quantification is for data compression, and the LDA, latent dirichlet allocation, or autoencoder, or Boltzmann machines. For reinforcement learning algorithm, we have the deep reinforcement, deep Q learning, the Q learning policy gradient methods, and there is another like a policy gradient method called the reinforce. So these are, and then for the playing the board games and the StarCraft 2 and the poker game, they all use the deep reinforcement learning. So then exactly what is deep learning? So deep learning is one of many research areas in machine learning. So deep learning focuses on learning data representations using deep neural networks. Deep neural networks are just standard neural networks with many hidden layers. Deep learning can be applied to any type of learning tasks of machine learning. So in these 3 lectures, I will cover the deep supervised learning and deep unsupervised learning. I will cover the convolutional neural network, recurrent neural network, hopefully. And then for the deep unsupervised learning, I will talk about the deep autoencoder, deep generative models, but I will not talk about the deep reinforcement learning, AlphaGo or AlphaZero. Since the deep learning is a modern name of neural networks invented decades ago, so I will review the history of neural network and introduce backpropagation in the next half of this lecture. So this is a cartoon picture of the human neuron, and in a human neuron we have the dendrites, and then we have the axon and the axon terminals. So you can see that the dendrites receives the information from other neurons axon terminals, and then this neuron will decide whether to fire or not, depending on the inputs it received from other axon terminal, other neurons. So the signal received by this neuron passes a certain threshold, and then this neuron will fire, and then they will send the information to some other neurons through these axon terminals. this is the cartoon of the human neuron. We can mathematically simulate this neuron. This is an artificial neuron. And you can see we have the inputs, and then we have the bias term, and then we have a nonlinear activation function here, and then this is the output. So if the received input pass is above some threshold, and then we will fire some signal, and then we will output some signal. If the received the sum of the inputs is below some threshold, we will do nothing. We will output 0. So then this is the mathematical model of the neuron. The output, the bias term, and the connections. This is the weights, connection weights, and this is the input from some other neurons. So this so there are many kinds of neurons. One important neuron is called the binary threshold neuron, proposed by Mark-Pitch in 1943. We can view it as the first generation of artificial neural network neuron. So in this binary neuron, they first compute a weighted sum of the inputs, and then they send out a fixed size, the spike of activity. It is a 1 if the weighted like a sum above some threshold. So instead of just using this kind of like a non-differentiable thresholded activation function, we can also using some other activation functions, for example, a sigmoid. So the sigmoid activation function will look like this. This is the input of the sigmoid activation function, and this is the output. You can see, and then at 0, the sigmoid output unit will output of 0.5. And then if the received input is very small and then negative, and then it will be like the output will be 0. If the output is very big, and then it will close to 1. So this is it has a nice probabilistic interpretation because the output of a sigmoid neuron is always between 0 and 1. So you can think about the logistic regression is the linear regression with a sigmoid output neuron. So in 1958, Rosenblatt invented an algorithm called the perceptron. It is a linear neuron. So the learning algorithm for the perceptron works as follows. It will always output 1 or 0. So first, they initialize the weights of, because it's just a linear neuron, just like this. It's a linear neuron here. So at first, they initialize the weights and the threshold to 0 or some kind of random, very small random values. And then the second, for each example, I in the training set, they perform the following steps. So if the data point I is corrected, it can be corrected, when we perform this kind of like using the sum of the, because the linear neuron is just a linear regression with the activation. And then if the output is correct, they will just not do anything. They will not update the weights of the linear neuron. If the model incorrectly outputs 0, actually this data point is 1, then they will add the feature vector to the weight vector. If the model incorrectly outputs 1, if the real output is actually 0, they will minus the feature vector of the weight vector. They will repeat this kind of step until some convergence criteria is met. So it's kind of like a simple, right? And then if your prediction is correct, don't do anything. If your prediction incorrectly outputs 0, just add it. If you incorrectly output 1, just minus your feature vector. So there is a intuitive explanation why this kind of perceptron, Rosenblatt's like perceptron algorithm works. Because you can think about each training data point as a hyperplane. So to get all these kind of training cases right, we need to find a weight vector on the right side of all the planes, right? So there of course, there may be not such kind of vector we will talk about later. So if there are any weight vector that gets the right answer for all cases, these kind of vectors, they must lie in a hypercone with its apex as the origin. Okay. So because the average of two good vector is also good vector, because if one weight vector can perfectly classifies all these kind of data points, and then of course these two good vector, when you average them, is still a good vector. But when each time the perceptron makes a mistake, the current weight vector must move to decrease its square distance from every weight vector in the feasible region. So the square distance decreases by at least the square length of the input vector, because you either add the data points to the weight vector, or minus the feature vector of the data point, right? Because you know that if such kind of like a weight vector exists, and then when you do this, it must converge there. But the thing is that how much it will converge, because every time you only add the data point or minus the data point, if you calculate the square distance, of course, the square distance decreases by at least the square length of the input vector, just because you add or minus the data point feature vector. So after a finite number of mistakes, the weight vector must lie in the feasible region, if the region exists there, right? Because we know that if the region exists, when we add the feature vector, it must converge. It must be able to find out these good weights, because any good weights like added up is also good weights. It's if the current data point is wrong, and then I move it to the good weights, of course, it will finally converge your good weights in this kind of feasible region. So this kind of like a perceptron algorithm get a lot of media attention at that time in the 1960s, I would say 1950s. So the New York Times says they demonstrated, the Navy last week demonstrated the embryo of an electronic computer named the perceptron, which when completed in about a year is expected to be the first non-living mechanism able to perceive, recognize, and identify its surroundings without a human training or control. You can see people are like put high hope for this kind of simple linear like a perceptron, or say linear regression model at that time. However, the perceptron can't even solve the XOR problem. For example, in the XOR problem, we have when the inputs are both 0, our output is 0. When both inputs are 1, we also output 0. When the inputs are either 0, 1, or 1, 0, we output 1. So it's easy to understand why the linear perceptron cannot solve this kind of XOR problem. If you look at this kind of like the labels of the red, 0, 1 and 1, 0 is one class, right? 0, 0 and 1, 1 is another class. So the linear perceptron is just a linear algorithm. We know that it's just draw a hyperplane in this space, right? To separate this, because it's a linear hyperplane is just a line in this two-dimensional space. You can never linearly separate this because this is one class, this is another class. There is no linear like a hyperplane, a line can separate this, these two classes, right? So that it's easy to understand. So, and then Minsky from MIT published a paper saying that suppose we just use the binary give an example like this. This is a pattern A. This is a pattern B. You can see pattern A and pattern B are different, because this is 4 pixels are like this, and this 4 pixels are like this, and then 1 pixel here, 1 pixel with 2 pixels in the middle. But here there are 2 pixels. But then Minsky and then showed this example, said, well, although a lot of people are so excited about the linear perceptron, but they cannot even solve this kind of like a pattern because they cannot, classify the pattern A from pattern B, because this kind of translation from the patterns can translate with wraparound, and the patterns with wraparound form a group. So it's easy to see why this the linear algorithm cannot solve this these two patterns, right? Because you see the linear algorithm always receive like a 4 inputs for like a you will add up the 4 weights of your linear weight, and then this pattern B also activate 4 weights, because it's a linear algorithm. Each time pattern A activates 4 weights, pattern B can also activate 4 weights. Of course, there is no linear algorithm can distinguish these two patterns. I will leave the proof as an exercise. You can think about it after the lecture. So there is some explanation here. So, but this result, the Minsky's result, is actually devastating for the perceptron, because the whole point of pattern recognition is to recognize patterns despite the transformations like a translation. But Minsky and Popper's group invariance theorem says that the part of the perceptron that learns cannot learn to do this if the transformation form a group. The translations with the wraparound shown in the above, like pattern A and pattern B, actually form a group. To deal with such transformations, a perceptron needs to use multiple feature units to recognize transformations of informative subpatterns. It means that we need some kind of like a hand-coded feature or nonlinear transformation. This is, beyond the capabilities of linear perceptron. So, and Minsky's argument is that if you hand code this kind of feature detectors, or then it's not the learning problem anymore. The perception, because you already know the ground truth, how to make it separable, and then you just and then you need to handcraft your features, and then that's not machine learning. It is a feature engineering. So basically, it means that to solve a problem, you need to have enough domain knowledge about your problem to make sure that your problem can be linearly separable. Then then perceptron will be useless, because it's not learning. Its success depends on your domain knowledge. It's still like a programming your computer instead of letting your computers program by themselves. So that's why in 1960s, people just use the handcraft features. So networks without hidden units are, for example, the Rosenblatt's linear perceptrons are very limited in the input and output mapping, because they can only learn the linear models. And then more layers of linear units do not help, because it's still linear. So the fixed output non-linearities are not enough, because because they cannot separate it. For example, the pattern A and B, they cannot be separated by the linear algorithms. No matter what kind of like nonlinear functions you added to the output, it doesn't help either. So what we really need is multiple layers of adaptive nonlinear hidden units. But how can we train such nets? So we need an efficient algorithm to adapting all these weights, not just the last layer. So this is very hard. So learning the weights going to the hidden units is equivalent to learning features. This is very hard from just think about it. And then it's this is difficult because nobody is telling us directly what the hidden units should do, right? So in 1985, Jeffrey Hinton and his colleagues invented the backpropagation. So the backpropagation is so important just because it can make the neural networks learn by itself, because they introduce the hidden layers with the nonlinear hidden units. So the nonlinear hidden units can learn by themselves. So what they do is that given an input vector, and then you pass through this input vector with a neural network with multiple layers of nonlinear hidden units, and then you get the outputs, and then they compare the outputs with the correct answer to get the error signals. Then they backpropagate this error signal to get the derivatives of the hidden units, the error signals for the hidden units. And then they can backprop the hidden unit, the error signals from this layer to this layer, and then finally to these connection weights. So thereby, the deep neural networks can learn the features, can learn everything by themselves. So the benefits of multi-layer perceptron with backpropagation is that the backpropagation allows the neural network to design their own features and the multiple layers of features adaptively. There is no domain knowledge, not just as Minsky criticized. You need to know your problem well, so you handcraft your feature, and then your network doesn't, your learning algorithm doesn't do much. But here, this is the contrary to that, and then you just show the deep neural network and then some examples. You just compare your output with the real target, and then they can use the error signals backpropagated to learn these kind of like hidden layers, and then to learn these features. So that's why the backpropagation is breakthrough in deep neural network or in deep learning. So this is a linear neuron in a matrix form. You just multiply the input X with the W, and then you have some kind of like this is the backpropagation, the delta rho for the linear neuron, and then this is your error function. Say your error function is the squared residues, is the mean squared error, or it's the squares residue summed over all training cases. Now you differentiate, differentiate to get the error signals for the weights. You get the derivatives of your error function, objective function, with your output unit, and then you get the derivatives of your output with respect to the weights, and then you use the chain rule of the differentiation rule in the calculus. You can guess, you can get the derivatives of your objective function with your weight W. See, just like this, multiply them together. So the Bayes delta rho changes the weights in proportion to their error derivatives summed over all training cases. So for the sigmoid logistic function, you just do the same thing. You first, get the error derivative, with your output unit Y, and then you calculate the gradient or the derivative of your output unit Y with respect to the input of this logistic unit neuron, and then you just multiply. And then if you want to get your objective function, this is some kind of technical details, and then how to derive the derivatives of your logistic neuron output with the input of the logistic neuron. You can check the lecture slides, after the course. I will not talk about detail here. So basically, the idea is that you need to use the chain rule to get the derivatives needed for learning the weights of your network, and then including the weights for the linear neuron, for the logistic neuron, or the deep neural networks for multiple layers. So the idea behind backpropagation is that we don't know what the hidden units ought to do, but we can compute how fast the error changes as we change the hidden activities, because this is the intuition behind the backpropagation and how the backpropagation is discovered. So when you first give you a problem of a deep neural network is the hidden units, you don't know how to do it, right? And then I think Jeffrey Hunter and his colleagues first found out, of course I don't know how to learn these kind of like hidden features adaptively, but I know that when I change the hidden units, I can check how my output changes, right? And then if I know how my output changes, and then I will know how my error signals will change. Means that how my output will fit the real target. I will get the error signals for my for my output, and then when I backpropagate it, and then using a gradient, using a chain rule, I can understand, I can get the error signals from my hidden units. When I get the error signals from my hidden units, then using this kind of, because each hidden units can be considered as a simple neuron, right? And then you can get the gradient with respect to your weights connecting, inputting, connecting to these hidden units. This is, I think, this is the underlying, intuition and how the backpropagation is, is discovered. So this is a sketch of the backpropagation algorithm. So you have your first you have your objective function like loss function E, and then you compute your loss E with respect to the the output units. And then after because the output unit is connected to the hidden layer, you can compute the derivative of your output units with respect to the hidden units connecting to these output units. And then using the chain rule, I multiply them together, I will get my derivative of my objective function or my objective loss, objective function E, and then with respect to the hidden units. Because each hidden units can be considered as a simple neuron. And then when I get the error signals or the derivatives of the objective function with respect to each hidden unit, I can easily get the derivative of the objective function with respect to the weights of these weights, and then just use the chain rule and multiply them together. Here's the details, right? And then you get the derivative of E with the ZJ, and then gets the derivative of ZJ with respect to YI, and then the derivative of E with respect to YI is just multiplying them together based on the chain rule. And then for the weights, it's the same. Okay. So this is the basic backpropagation. So actually, the backpropagation can be done in a computational graph. For example, you have you just view as each node, each variable, and then as each input, say X. My input here is A and B, and then you just like you see the hidden units are C equals A plus B, and then D equals B plus 1. My output units is actually E equals C times D, right? And then you can, if you use each variable as a separate node, you can, because for each step, the derivative of C with respect to A can easily compute it, right? Can be easily computed. And then, following this kind of graph, and then just we can easily, compute the derivative. We just like easily get the derivative of the final output with respect to every internal node by either forward pass or backward pass. So here, it's shown here. So A equals 2, and then C, the derivative of C equals to A is 1, and then the derivative of C with respect to B is 1, and then but the derivative of E with respect to the C is 2. When we want to get the derivative of E with the A, easy, just like follow this path, you will get it. And then the same thing here. So this is how the backpropagation then can be in a computational graph. So look at the backpropagation in a more complicated computational graph, because in deep neural network we have multiple paths, right? And then this is input, hidden layer, output, and then you can see like it's the same thing here. You can either use a forward mode differentiation or the backward reversible differentiation. It's the same. So basically, we need to get if we use the forward mode differentiation, I first need to the derivative of X with respect to X is 1, and then we get the derivative of Y with respect to X, and then we calculate the Z with derivative of the output Z with the hidden unit Y, and then we multiply them together, and then this is a forward way, and then 1 multiply this alpha plus beta plus gamma, and then here, because this is a linear like fully connected. You can see it's a fully connected layer with 3 weights. And then of course with the forward mode, and then the output unit Z with a derivative of the output unit Z with respect to the input X is just multiply them together. See, I don't need to, enumerate all possible paths because I just need to, first I need to get the derivative. This graph shows that although, you can see there are many different paths from X to Z, right? You can see here and then here. You can either take the alpha and then epsilon or beta and then gamma. But fortunately, we just need to, the computation can be done locally. So then we can just like a chain them together to get the gradient. This is just want to show that. Using the reverse mode, it's the same thing. We can chain them together. Every computation can be done locally in the computational graph. Okay, this is the benefit of the backpropagation. So there are some criticisms about the backpropagation. The first, it requires a lot of labeled training data, but in reality, a lot of data is unlabeled, and we know that the brain needs to fit about 10 raised to the power of 14 connection weights in only about like 10 raised to the power of 9 seconds, about like 100 years of the human life. So unless the weights are highly redundant, we have so limited label information, we cannot possibly, provide enough information to fit all these kind of weights in like we use the analogy of the human neural network, right? And just because you only, you don't have enough like label information to fit so many different like connection weights. But how, why humans can learn, so efficiently? It doesn't require backpropagation. So this is the criticism about backpropagation. And another criticism is that the learning time doesn't scale well. Because in the 1980s and then even in 1990s, it is very slow to train the deep neural network with many hidden layers. But nowadays, it's not a problem anymore because we have the computers millions of times faster. And the neuroscientists, some neuroscientists, criticize the backpropagation is not biologically plausible because it needs to send the forward pass, and then give the input, you just like do the forward pass to compute your output, and then you do the backward pass, and then you need to backward to calculate the gradient, right? The derivative of the output with respect to the hidden layer, and the derivative of the hidden units respect to the another layer of a hidden lower layer hidden unit, and the backpropagates the lower layer hidden units with respect to your input, and then you get the gradient of everything. But in human, we don't do that. It's not, there is no scientific evidence saying that, humans using the forward pass and backward pass to do like, to train your brain, right? So that's why, some scientists criticize this not biologically plausible. But I'm not sure, this is important for deep learning, because even if my personal opinion is that even if it's not biologically plausible, but it doesn't matter. And then because the computers are different from the human brain, right? And then they are completely different worlds. So then I will talk about some kind of like, and in 2015, actually, in my master thesis supervised by Jeffrey Hunton, we actually, train a deep neural network with 5 layers, and then it is a regularized autoencoder. For example, you give the input image of digit 100 written digit 4, and then you input 200 hidden layers, and then you embed it to another 20-dimensional space, and then you just try to embed to embed to another 100 layer, and then finally you want to reconstruct the original image. You just minimize the reconstruction error. You compare your output 4 with the original pixel input 4 and minimize the reconstruction error. At that time, the computer is very slow. It's actually like takes a month to train the algorithm on like 3,000 minutes digits. you can see how slow it is. But nowadays, I can train, these 3,000 digits, I think in half a minute or even 1 minute. So you can see the computers are like a million of times faster than that. So in 2012, we talked about the ImageNet challenge, and then the NEC Labs America champion with the error rate of about like close to 30% in 2010. But in 2012, they reduced it to about 15% by Jeffrey Hunton's group using this new network. So what is the secret recipe in this deep neural network? Actually, they just use a different activation function called the rectified linear. So instead of using a sigmoid function that causes like a saturation, they use and gradient vanishing. They just use this rectified linear unit. So then the gradient of this rectified linear activation function is always 1. So it will never vanish. So then a natural question is that what makes deep learning revive, and then why deep learning is so popular? Why it is not popular say 10 years ago, right? And then because as we talked about, the deep learning is nothing but the modern name of deep neural networks, right? And then so why now? And then there are some reasons. First of all, we have a good model because the deep neural network has the intrinsic advantage of learning hierarchical distributed feature representations. The model capacity is huge, and then and also the powerful computers and the big data enable us to build the models with a huge capacity. And then traditionally, we can build a model with huge capacity with many different layers and make the many millions of or billions of weights, but we cannot train it, right? Because the computers are so slow. But now the computers are millions of times faster, and we have 1.2 million training data points in the ImageNet challenge. So we can use the powerful computers and the big data to train this model efficiently. And then also we use some kind of tricks called like a data augmentation. We can augment the data. And another important discovery is about the batch normalization and rectified linear units, so that the training algorithm can efficiently backprocess the error signals from the output signal to the hidden layers and then to the inputs. And another reason it is popular because we have very popular or user-friendly tools, for example, PyTorch, and then the TensorFlow, and or even this Torch and Cafe, or I would say data is not important anymore. So in summary, so the ongoing AI revolution, and then with many different amazing applications, are actually driven by the deep learning. Deep learning is nothing but a new brand name for the deep neural networks. So actually, it's the deep model plus the big data plus the powerful computers leads to the success and the successes of deep learning. So I end this lecture by a quote by Professor Pedro Domingos from University of Washington. So learning is more like a farming, so which lets nature do most of the work. Farmers combine seeds with nutrients to grow crops. Learners combine knowledge with data to grow programs. This is true for deep learning. So the deep learners should combine their knowledge with large-scale data to grow their programs. They should encode the essential knowledge into network architectures. It's called and also into data. So it's a network engineering, like different network architectures, like a ResNet or like AlexNet or GoogleNet, or like other network architecture. And data engineering, for example, that's a data augmentation, right? We should let the back propagation and stochastic gradient descent do the heavy lifting. Okay. Thank you. So the next lecture, we will talk about the supervised deep learning with convolutional neural network and recurrent neural networks. Any questions?
Any questions from anyone? Well, actually, I have a question for you, Ranquin, while you're there. You know, I know, I sort of know this, but I just guess I was following your lecture. And so when they went from the Rosenblatt, wherever that is, well, like the perceptron, to having, I guess, many layers, that was the next thing and so forth. Just go through again what what you get from like the perceptron when you're doing that, you can't solve these problems, but then you have to add in layers, and is that what I think it's a little past that, right? I mean, it's probably like 45 or something.
Okay.
Yeah, so here's the perceptron is coming up here in a second, right? That's right there, yeah. Yeah, and then you can't, there's
Here.
but then, yeah, explain it. So then they introduced the idea of the many layers. Is that the next thing?
Yes. Oh, I got it. I know what you're talking about. I think it's here.
Yeah.
Yes.
So yeah. So this was the kind of the next step is they introduce layers. Was that what this is?
Yes. So the perceptron is just a linear classifier, right? Nowadays we look back and then just linear classifier.
Okay.
And then with a special training algorithm. Currently, when training a linear classifier, we probably use a lot of optimization algorithm. But at that, in the old days, they probably don't know that they need to use the optimization to do it. They just using the add. When we make the mistakes, they just add the input or minus the input feature vector, right? Because their weights has the same dimension as their input feature. Then the people realize that it's a linear classifier, and then you cannot do much. For example, even for this kind of like a XOR problem, you cannot solve it. You really need to introduce the non-linearity there. And then how they introduce the non-linearity, they said, okay, I just need to handcrafting more features so that this problem is linearly separable. For example, in the XOR problem, they just introduce additional like a nonlinear feature x1 times x2, right? When you have the x1 times x2, and then this problem becomes linearly separable.
This is kind of like a support a vector machine in a way. That
yes. Okay. In a support vector machine, they use the kernels to introduce this kind of like a nonlinear feature representation. So they say with the kernels, they're induced feature space by the kernel is infinite dimensional. That's why they can always find a linearly separable hyperplane, right? That is the idea, like a kernel SVM.
Okay.
So that's why they introduced yes, you're right. They introduced the layer, but they introduced the layer must be hand coded by the user. The problem is that when you give me a bioinformatics problem, for example, classify this transcription factor binding gene and this transcription factor from other like non-transcription factors based on some sequences, and then how can I know what kind of features should be encoded there, right? It's impossible. And then we only know that this is like a regulator, and that's a non-regulator. That's a target. But I don't know like what kind of essential information should be there to distinguish the regulator and the target. If I know, and then I already solved my problem, right? But for perceptron, you must know that. If you don't know, and then you cannot solve your problem. But when you have the hidden layer, and then it's not handcrafted, and then you just provide this is the input features of my regulator. This is the input feature of my target, and then I just provide the output, and I train on enough data points. My algorithm will figure out how to combine this x1 times x2, or actually it's x1 divided by x2 to get the true answer. This is the power, of the hidden, introducing the hidden units.
But Ranquin, the thing I have to say, I'm just still not understanding when I look at this figure is where do I see phi 1, phi 2, phi 3 on the left-hand side, and then I see layers on the right-hand side. How do the phis end up making the hidden layer? That's what I don't really understand. Like, how do you go from needing these handcrafted features to suddenly you have a hidden layer? Like, is that obvious?
I would say it's not obvious because they just say, this is your original input, right? The original input, you need to define some kind of feature so that you can apply that kind of perception algorithm so that so then your algorithm can solve your problem, right? So then
but you mean just one of those middle nodes in this particular thing here, one of the middle nodes is x1, x2, like input is x1, x2. But then one of the things is x1, x2 is a middle thing, right? Is that right or no?
This is your input, right? And then you can think about this is a phi 1, phi 2, phi 3, phi 4 or something.
Yeah.
You need to code it by yourself. Then, because at that time, people don't know, right? They just draw a cartoon picture like this. I think Jeffrey Hinton was inspired by this kind of thing. Well, this is not user-friendly. This is not good. And then how about let's don't hand code this layer and just still use this cartoon picture, and then just let the algorithm try to figure out what should be put here. And that's why how the backpropagation algorithm was discovered at that time.
Oh, okay.
That's why
no, but just my understanding. So to go back to the figure more second. So the point is that just go back to the XOR for that figure. So the key point is in this figure, I was getting a hard time mapping it, is that the bottom is x1 and x2. That's what comes in, right? Yes. And then the middle layers are, one of it is just phi of x is x1. It's just x1 again. The other was x2 again. But then there's a third unit will say x1, x2. So you have 3 units, and then those units then get combined to make the classifier for bomb and toy, right? Am I getting this correct? Okay. Oh, I get it. Okay, and then and that I just took me a little while to understand.
That makes the perceptron work on this example. Because you handcrafted features so that they are actually separable. They will find. Because the perception algorithm is not guaranteed to work, right? Sometimes it will fail because they cannot find any weight. It will not converge. So when it converges, it will find this algorithm. When it converges, it means that your problem is linearly separable. But they just like you need to design these features, hand-coded features, so that it is linearly separable. So this is, but this is not good. But it inspires the next generation of machine learning researchers to design a deep neural network.
Oh, okay.
That's why I showed this picture. No,
that helps. Very good. Any other questions from people on this stuff?
I'm sorry. This lecture is just for the introduction, and then for the general idea and why. Or how the deep neural network, evolves from the most basic linear perceptron to this current stage and then becomes so powerful, and why the deep learning, is not that popular like 10 years ago, right?
Okay.
Okay, thanks so much. So maybe
thank you very much. Great job, Ranquin. So I guess we're good people, and we'll just resume.